And today we're going to be talking about efficiency and how that relates to a system. We'll define what a system is here in a minute, but before we get started, I would like to introduce you to a couple of interesting facts that will help lead us into our discussion today. You and I are both sitting on a very big question, and it's the same question, and it's an interesting question that is becoming more and more relevant in today's business world, and that is, do we have an energy problem? If there's no problem, there's no need to fix anything, right? But if we look at the amount of energy consumption and compare that to the population, we can see some interesting facts. The world population has been growing steadily for the past 100 years, but it's a very controlled growth. If we look at the amount of energy consumption compared to the population, it's exponential, and it has been growing increasingly at an increasingly larger rate for the past 100 years. For the amount of electricity that's consumed in the entire world, we average about 18 million gigawatt hours, and that was a few years ago. Can you imagine how much of the world's electricity consumption was the United States alone? It might be of no surprise to you that we were up there. About 25% of the world's electrical energy consumption was right here in the United States. So a lot of energy is being used. There's a lot of chances to reduce the amount of energy that we use, and we can do that by becoming more efficient. So the next thing I'm going to talk about is, what is power loss? We have a certain amount of energy going into we'll call it a black box system. It doesn't matter what the system is, but we have some energy going in and we have some energy coming out, or power coming in and power coming out. The amount of power or energy that is lost, that is an inefficiency. So we have some ways that we can try to minimize this lost power. Another way to look at this power is the output power is equal to the input power minus our power losses. And we'll use that equation here in a second to kind of shed some light on some different things we can think about with efficiency. A lot of people know that efficiency is a ratio of the output power to the input power, and efficiency is a good measure of how well something utilizes the input energy. But what may be of a better concern is thinking about power loss as an absolute value, because that's really what we're trying to minimize, the amount of power that's needlessly turned into heat and not used to a good end purpose for your application. And just so you know, throughout the rest of this presentation, I'm going to be using the Greek letter eta for a symbol for efficiency. If we can take these power losses and reduce them or minimize them, we can increase our efficiency. And that's really the goal here, is what power is being lost, how is it being lost, how can we minimize it or get rid of it. That's what we're going to be taking a look at. And we're going to be looking at a system, an entire system. A lot of people think of a system as maybe a motor or a gearbox, or a motor and a gearbox, but I like to think of a system as a complete package. The input power, a variable frequency drive or an automatic speed drive, they all go by different names. I'll be referring to them as a VFD, or a variable frequency drive here. The output of the VFD goes to the motor, turns the motor turns the gearbox can turn a transmission element like a chain or a belt, or directly coupled to the application, which could be a conveyor or a hoist or anything like that. That's an entire system, and we're going to break a system down into its individual components, see where we're losing power and how we could possibly affect that. But before we do that, I just want to give a brief overview of where can we save energy, where do we have the most potential to save energy. If we look at the three main things that people think of, high efficiency motors or premium efficiency motors, that's been a big concern with the EPAct law and also with the new EISA law. I'll explain those a little bit more later on in the presentation. But there's some other things we can do. By introducing a VFD into the system, we can control the speed of the motor, vary the speed, rather than running it directly off the mains. And we also have mechanical components. We have a potential to save some energy with all three of these components, but by far the largest impact that we can make is with the mechanical components. And remember I said there's a potential energy savings in percentage, they're relative. Just by using an energy efficient motor you may not be saving energy. Just by using a VFD you may not be saving energy. So we'll take a look at these things and see when does it make sense to use these components and how do we use them to our advantage. Every system has different components. We've been talking about that for a couple minutes. You have your input power, your variable frequency drive, your motor, your gearbox, your transmission element, and then you have your load or the application that you're trying to move. Each individual component has losses. Nothing is 100% efficient, and definitely nothing is greater than 100% efficient. Einstein kind of proved that that's impossible. But what's really interesting is, do you know that how these efficiencies relate to each other? The effect is actually multiplied. So each little inefficiency is multiplied throughout the system. So you could have a really good high efficiency motor with a directly coupled to your load, but if you have a poor efficiency gearbox in between there, you lose all the benefit of buying that premium efficiency motor, that high efficiency motor. So that's something that we need to take a look at and try to fit into the big picture of our system, look at all the individual components and see, do they make sense adding together? Well, not adding together, but multiplying together. Just for an example, if we looked at an ideal system where every component was 99% efficient, if we had our 6 components here, that they're all 99% efficient, when you multiply those together, our maximum efficiency is only 94.15%. That's throwing away over 5% of our power, almost 6% of our power, just to energy losses, to heat. And that's with an ideal system that's very efficient. And if we look at a typical system efficiency, which, and I selected some really good efficiency components here actually, multiplying these together, it's almost 80%, creeping up on 80% efficiency. And that's pretty good. But one of the things you can think about is if you can eliminate some of these components in between there, maybe you don't need a transmission element, maybe you don't need a belt to couple the gearbox to your conveyor. If you get rid of one of those elements, you can get rid of one of the inefficiencies and make your entire system more efficient. So now we're going to talk about each component. We're going to start with the electrical power system that's going into the inverter. The electrical system that feeds the inverter, or the motor if you don't have an inverter, is going to have some losses. You're going to have copper losses, you're going to have some reactive power losses, some harmonic losses. The two main losses that we're going to concentrate on, well, the main loss that we're going to concentrate on is reactive power, because that's something we can actually do something about to help minimize those losses. But the main loss in the electrical power system is the copper losses. And that's the amount of heat that's created when current flows through a wire. If current flows through a wire, it heats up. That heat is lost energy that could have been used for something else. So one way you can minimize your copper losses is by selecting the proper cable size. If your cable is too small, it increases the resistance, and that's going to increase your copper losses. So that's one way that you can minimize your copper losses and your electrical power system losses, is by selecting the proper size of wire, the proper gauge wire. Now the next thing that we're going to talk about is reactive power. Well, what is electrical power, first of all? Well, it's the product of voltage times current. And if you look at the picture up here, you can see that when the voltage and the current are in phase, and by in phase I mean that they go up and down at the same time, they both cross the 0 point on the x-axis simultaneously, and you can see that's the case with this particular example here. When that happens, all of the power is positive. That means all of the power is being used by the load, and that's a good thing. when your voltage and your current are in phase. If they're not in phase, the difference between those is called a phase angle, and this can also be thought of as a power factor. I know you guys have heard of power factor before. That's kind of what it means. The voltage and the current are out of phase with each other. And what happens here is when you consider the electrical power of a system that has the voltage and the current out of phase with each other, when those are multiplied together, a positive times a positive is a positive, so that's good. A negative times a negative is a positive, that's also good. But when you got a positive times a negative, it makes a negative. When we have a negative power, that is power that is lost. It is returned to the line, and that's an inefficiency for you as an end user of electrical power. Well, what can we do about this? How can we correct this? Well, we're concerned about that phase angle. We want to get rid of it. Well, first of all, where did it come from? Why do I have a phase angle, and how can I minimize it? If we think about it in relation to a power triangle, there are different types of electrical power. We have real power. That's what's really doing the work. That's your kilowatts, or your horsepower. That's your real power rating. You have apparent power, which is just basically that's what you're paying for. When you have an electric bill, you're paying for the apparent power, the amount of power that the power company sent to your house. That's how much you're paying for. If you have reactive power, well, guess what? That contributed to your apparent power, but you weren't able to do any work with it. It was just reactive power. It's what we're wanting to do is try to minimize that reactive power and make our apparent power equal to our real power. That way we're only paying for what we use. That's the end goal. If you look at a capacitive load, the power factor is actually leading a little bit. That means that the current is leading the voltage. This doesn't happen too often in industrial loads. This can happen sometimes with inverters or with some types of computers, but usually loads are inductive, like a motor, a coil. You know, the coils inside of the stator, they're an inductive load. Lighting ballasts are inductive loads. The majority of industrial loads are inductive. So our power triangle is going to look like this. It's going to be below the x-axis. Well, how can we minimize that amount of reactive power? Well, if our power triangle is going below the x-axis, like with an inductive load, what we can do is add some capacitance to it. So we have this power triangle with reactive load. If we want to minimize that and also minimize our apparent power, minimize the amount of energy that's not being utilized properly, we can add some capacitance to the system, and these are called power factor correction capacitors. You may have them in your plant. That's what they do. They minimize the phase angle difference between the voltage and the current, trying to make most of the power positive and being used by the load as real power. So that's one way that we can help out with efficiency, is minimizing our power factor on the electrical side. Now that electrical power is going to feed into our inverter, and that's the next thing that we're going to talk about, is our variable frequency drive. Alright, the next portion of our system we're going to be talking about is the variable frequency drive. Now, a lot of people are under the misconception that if you add a variable frequency drive to your system, you're automatically more efficient. Well, that's not true. If you take an existing system and you don't change anything else, all you do is add a component to it, doesn't matter what component you add, there's going to be an inefficiency that you're adding to the system, and that gets multiplied for your entire system, and you're going to be losing energy. A VFD doesn't magically operate without any power loss. Of course, there are power losses inside of a VFD. They get hot when they run, so you know that some of that energy is being transferred to heat and not being used. But you do stand to make other gains when you add a VFD. So when you add a VFD to a system, you can gain energy, but it's in the way that you operate the motor. So we'll talk about those different things and how you can save energy in your system by introducing a VFD into it. So a VFD has the same losses as almost any electrical component. There's going to be copper losses. Everything that's electrical has copper losses. There's current going through wires, or in this case, they're going through the traces on the circuit board, and they create heat, and that's a loss to energy. There's switching losses. That's a little bit different. With an inverter, we have output transistors. They turn off and they turn on. That's going to be a loss. And a little lesser known fact is that inverters also introduce some harmonic losses to the motor. That actually decreases the motor efficiency. So we'll talk about how does that affect my overall system as well. If we look at the basic parts of an inverter, we have our AC power that's coming in. That goes into our input rectifier that gets changed to a DC voltage. And the control electronics of the inverter actually sends out DC pulses to the motor. And if you look at the output of the inverter up here above my head, you can see the little black boxes are the DC pulses. The red line is actually the average current level. So the black boxes are the voltage pulses that are coming out of the inverter. The different sections of the inverter have different losses. The input rectifier, you're going to have forward biasing power losses in there. You're also going to have some of those losses in the output section, but the main loss of the output section is the switching of the transistors are turning on, they're turning off. It's like a switch, and they're going to heat up every time you turn them on and turn them off. And there's also, those losses can vary because you can change your switching frequency, and that is how fast you turn your transistors on and off. You may have heard of 4 kilohertz, 16 kilohertz, or a 32 kilohertz switching frequency. When you read about a switching frequency, that's what they're talking about. How fast are those output transistors turning on and turning off? And I'm sure you can imagine, the faster that the output transistors cycle, the faster that they have to turn on and turn off, the more energy that they're going to lose in the form of heat. Now if we look at the third section, the control electronics section, that also has losses. You have processors inside of there, you have resistors, you have inductors, you have capacitors, LEDs, you have all of these different components. There's a switch mode power supply that makes 24 volt DC to control everything. All of these components use energy. All of these components are going to create a little amount of heat, but if you have hundreds of these little tiny electronic components, they all add up to some portion of energy loss, whether it's 1 watt or 2 watts. It still has to be taken into consideration. So there are losses inside of a variable frequency drive. But usually, variable frequency drives are very efficient, relatively speaking. 92 to 98%. The efficiency of a variable frequency drive actually depends on its power rating. Because we have those losses in the control section, basically the computer part of the inverter, as the inverter gets larger and larger and larger, the losses in the output section are a bigger portion. So the control section losses are almost minuscule or insignificant compared to the overall losses. So the inverter has a higher efficient rating. The efficiency is actually a unitless rating, like we mentioned earlier before. But one of the ways that we can really save energy by introducing an inverter is by controlling the speed. Just putting an inverter in the system, or a variable frequency drive in your system, doesn't introduce efficiency. It actually introduces an inefficiency. Some other losses I talked about, it might make your motor more inefficient or less efficient, and it does. It's going to create some harmonic losses in your motor. What an AC induction motor wants to see is a perfectly sinusoidal voltage. It wants to see that sine wave signal that you're used to seeing for voltage. With these pulses, it creates harmonics, and these harmonics can add losses into your system. And it depends on the pulse signal. It also depends on your switching frequency and pattern. But we'll talk about that in a little bit when we talk about the motor. There's another potential power loss in the cable going from your VFD to the motor, and that's parasitic capacitance. Sounds fancy and important, but it's actually really easy, and it's more of a problem when it comes to electromagnetic compatibility or EMC problems. But as your frequency of your signal gets higher, the impedance of your cable goes down, because the cable actually starts to act like a capacitor. With your cable conductor in the middle, you can see in that picture above my head, and actually the rubber sheathing around the cable acts like the dielectric of a capacitor. So in between power cables kind of acts like a capacitor, and in between the power cables and ground, that also acts like a capacitor. So you could have some losses there. More importantly, it's an electromagnetic compatibility issue that you could have some interference with other components, but it could be a power loss in the system. So let's just review the VFD power losses real quick. The first thing is you can have harmonic losses in the motor, actually up to 10%. If we look at these curves, you can see the difference between the efficiency of a motor if you run it just on the mains, and on the mains I mean just putting AC power directly into it with no inverter, versus using an inverter or a variable frequency drive. The light blue line you can see is just a little bit lower, so it is a little less efficient if you use a frequency inverter, and this is what I'm talking about, the motor coupled with a frequency inverter. We also have some cable losses in between the inverter to the motor. We talked about that. We can have some parasitic capacitance losses also. The inverter has losses, so there again, there's another power loss in the system. But oddly enough, in the cable between your supply and the inverter, you actually gain some energy there. Remember when we were talking about power factor earlier? If you directly run your cable into the motor is a very inductive load. There's going to be a huge phase angle there, a big power factor, and you're going to lose some energy there to reactive power. With an inverter, it's like an automatic power factor correction. It actually has a slightly leading power factor, and you can save energy. You can actually save up to 20% of your losses on that cable in that portion of the system. So that's actually a gain that you automatically get by putting an inverter in. It does not weigh the other losses, but there are still things that we can do to save energy. And just to compare an inverter to mechanical variable speed control real quick, because there's a lot of people out there that don't use inverters. They have a friction disc type of variable speed control or a belt and pulley system. These are common mechanical ways to change the speed of the system. Remember, an inverter was about 92 to 98% efficiency, so we'll compare that to mechanical variable speed real quick. Actually, the maximum efficiency you can get out of a mechanical variable speed friction disc is 90%. As you change the ratio, as your ratio goes up and the output speed goes down, your efficiency drops off. So the maximum you can get is 90%. That's less efficient than an inverter right off the bat, no matter what you do. Same thing with a belt and a pulley. Has a similar operating curve, whereas the ratio goes up, your efficiency goes down. So they're not very efficient. Inverter is going to be a little bit more efficient than, well, not a little bit, a lot more efficient than a mechanical variable speed device. Some other things that a VFD can do, some advantages it can give you, is when you're ramping up to speed, when you turn on a motor that's directly powered from the AC line, it not instantly, but it comes up to speed, and there's a lot of work being done in the rotor. When you use an inverter, you can control that ramp and the amount of work that's being done in a rotor, and that's some energy that you can save. You can also save some energy on the deceleration side when you're stopping the load. You may have heard of regenerative energy. A motor and a generator are very similar in their construction, and actually when you decelerate an AC induction motor, it acts like a generator, and it pumps energy back into the variable frequency drive. Now what you do with that energy, that's up to you. Sometimes you can have a brake resistor where it just burns off the energy in the form of heat. Well, that's pretty wasteful. What you could do is maybe have two inverters coupled together. If one is starting when the other is stopping, that's a perfect chance right there to save energy. While the deceleration of one unit, it acts like a generator, pumps energy onto your DC link between the inverters. The other drive can be using the energy to accelerate. That's when you need the most energy, is during acceleration. So you can actually recover some energy losses if you couple the DC links together, or if you use a regenerative power supply. The way that those work is when your motor ramps down, acts like a generator, pumps energy back into your variable frequency drive. That energy can be sent to a regenerative power supply, which conditions the energy and sends it back on the line. That way it's not wasted. A regenerative energy power supply is usually it's at a premium here in the United States. They're expensive, but if you look at the long-term goals and the long-term gains you can achieve with this, they're they are worth the money. Another thing that a variable frequency drive can do for you is take a look at this system. We have a variable torque load, which could be a pump or a fan, anything that changes the amount of load as speed changes. These torque versus speed curves are for a 2-speed motor. Actually, you're changing between the poles when you operate. This is a typical way to control the speed before frequency inverters came along. If we look at the same system being run by a frequency inverter, there's a different torque versus speed curve for each speed set point. But what is very interesting is if you look at this, for every speed that's lower than the base or design speed of the motor, the way that the load curve is shaped, the motor is actually very underloaded. And when the motor is underloaded, we'll explore this a little bit more when we talk about the next step, which is motors. When the motor is underloaded, it's operating very inefficiently. So one of the things that we can do is increase the efficiency of the system by changing those torque versus speed curves. And the way we can do that is with a variable frequency drive. I not only have the capability of changing the frequency, I can also change the voltage. So by changing the voltage versus the frequency output of my VFD, I can actually tailor that torque versus speed curve to more suit the application. For example, this variable torque load, now for every speed set point that I'm running my motor, it's ideally loaded. I've lowered the curve to match my nominal torque rating of the motor at that speed, and that makes the system a lot more efficient. That's a lot of energy that can be saved there as well. So if we want to just look at a basic overall view, is that you can have a lot of gains with a variable frequency inverter. Alright, the next components that we're going to talk about are the motor and the gearbox. We're going to talk about the motor first, but the majority of all losses are heat, but especially in the motor and the gearbox. In an asynchronous motor, we're going to have some of the same losses that we've had for any electrical component. We're going to have copper losses. But there's a couple of other different losses in an asynchronous motor. You have the friction of the bearings, you have iron losses, you have eddy current losses, you have a bunch of different losses. But really the main loss that we can attack are the copper losses. And then we'll talk a little bit about how to do that in an asynchronous motor. Interestingly enough, in a synchronous motor, that means a motor that has permanent magnets on the rotor and there is no slip. There are no copper losses in the rotor, so inherently a synchronous motor is more efficient than an asynchronous motor. But for today's discussion, we're going to talk about asynchronous motors since they are by far used more often and they're less expensive than a synchronous motor, so there's just more of them out there. It could make a larger impact in our conservation of energy by attacking asynchronous motors. If we look at the relative losses in an asynchronous motor, the majority of the losses are copper losses. If you look at those two big orange bars at the bottom, those are your losses in the stator and your losses in the rotor due to copper losses. That's the current flowing through the motor, creating heat, which is lost energy. There's a couple of other things that you can see there, like in the dark blue at the very top, those are the friction losses in the bearings. We could put high efficiency, low friction bearings in the motor, but in the big picture, that's not really going to make that much of a difference. If we look at the other losses, like the copper losses, if we attack those areas, we can make a big difference. So how can we attack those losses, and how can we change the efficiency of an asynchronous motor? Well, there's two major ways. The first way is to use better materials. Most asynchronous motors have an aluminum squirrel cage in the rotor, and aluminum has a little bit higher resistance than copper. So you could use copper, which is a better conductor. It's a better material that you could make the rotor out of to reduce the amount of resistance, thereby reducing the amount of I squared R copper losses in the rotor. So that's one way. And you can see in the formula that I put up here, this is how the resistance of a material is related to its size and to what type of material it's made out of. Now the second way that we can make an asynchronous motor more efficient is by over-dimensioning. Now this may sound kind of weird, but let's think about it this way. Looking at this efficiency versus load curve, let's think about a car engine or a car motor instead of an asynchronous motor. Your car is designed to operate at a certain speed, and most of the mile per gallon ratings in the US are here. They're based off of 55 miles per hour. If you go faster than 55 miles per hour, you're going to use more gas. And if you go slower than 55 miles per hour, you're going to use more gas. You use more gas in the city than on the highway, and that's also due to starting and stopping. But you know, the big picture is that the efficiency of your motor changes at different speeds or different loads. The same is true for an asynchronous motor. If we look at this blue curve, the dark blue curve on the top, that shows us how the efficiency changes with loading. At 100% load, I have a certain efficiency, and then you see the curve kind of change a little bit. Actually, it really starts diving down when the motor is severely underloaded, and that's one of the things we were talking about earlier with an inverter. An underloaded motor is less efficient than a properly loaded motor. So what we can do is we can take, let's say a motor is rated for 5 horsepower. That would be 100% load, our rating. It has an efficiency of, let's look at this curve, say 85% is a good number for a regular standard efficiency motor of that size. If we were to underload that motor, if it was rated for 5 horsepower at 100% load, what if we only loaded it 60 to 70%? What happens to the efficiency? Well, if you look at that curve, you can see the efficiency actually goes up just a little bit. So what we do is we have a motor that's capable of, let's say, 5 horsepower, but we rate it for 3 horsepower to try to get into that sweet spot where the efficiency is a little bit higher. Now we have a more efficient motor. And another way you can think about it is, you know, if a motor is this big, doing a certain amount of work, it's going to heat up and get hot. A bigger motor that's capable of more work is not going to get hot because it can do a lot more. It's not going to get hot. That means it's not going to have losses due to heat, and that's our main source of losses that we want to get rid of. So how does increasing the efficiency affect a motor? Well, a couple of different things. If you use copper instead of aluminum, it's going to be heavier. Copper is heavier than aluminum. So the rotor inertia goes up, and copper is more expensive than aluminum, so the price is going to go up. The rotor inertia is also going to go up with a over-dimension motor because inertia is actually more affected by the size and shape of a component rather than the mass, because the size has a squared effect on the inertia. So there's a couple of different things that are gonna change. Our inertia goes up, so we can't start and stop the motor as fast or as often without heating up. It's going to be more expensive, obviously, and the thermal utilization is going to go down. That's just a fancy way of saying that it's not going to get as hot. You know, we're going to reduce the amount of losses that we have in that motor. So different things are affected. But remember, back in the first section we were talking about the relative potential difference we can make in changing components and saving energy. And by using a high efficiency motor, I told you it was something like 10%. Using a VFD, we could gain 30%. Changing mechanics, we could gain 60%. Well, if by using an induction motor that's of a higher efficiency or a premium efficiency, I can only save 10% of the overall energy of my system, is it worth it? Is it worth doing that? Well, one of the things you got to think about is an asynchronous motor only has 2 moving parts. It's 2 bearings. That's it. They're very solid construction. It's a very simple machine, and they last a long time. They last a very long time. Larger motors can last up to 20 years. So, is it worth it to have an increased efficiency motor in your system? Of course it's worth it, because of the lifetime of the motor. You're going to save so much energy, because 96% of the costs of an AC induction motor is used for energy, just to run the motor. You can imagine how much it would cost to run a 10 horsepower motor 24 hours a day, 365 days a year, and we'll actually go through a couple of those calculations later. But even though it's relatively a smaller portion of the gains that you can make, it's still worth doing it. most of the energy cost is in running the system. So when should you use an energy efficient motor? Well, you're only going to be able to save energy if you're running. So it's going to be a motor that you turn on and it's running all day or runs for a long period of time. It's going to be a motor that doesn't cycle. You turn it on and let it run. S1 duty, continuous duty. You want it to be loaded properly. Remember, we were looking at that efficiency versus loading curve. If it's really underloaded, my efficiency goes down. I don't want that. So you want your proper loading conditions. You don't want to be cycling your load back and forth all the time, and you want to have an application where you turn the motor on and you let it run. So now that we know when to use an energy efficient motor, when do we not want to use one? Well, the exact opposite. If the utilization is bad, like if the motor is really underloaded, if you're starting and stopping the motor all of the time, or if you have a low number of operating hours. If you only run this motor for 15 minutes, a half an hour, or an hour a day, when are you going to end up gaining gaining the money back that you put on the initial cost of the motor? Well, it's going to take a long time for that for the amortization to occur, and it's not going to be worth it for you. So you also need to know when you shouldn't use an energy efficient motor. And just to briefly touch on some of the laws that we have here in the United States concerning energy efficient motors. There's a law called EPAct. It's the Energy Policy Act, and that went into effect in 1997. It was written back in 1992, and that law basically says that all motors that we use in industry need to be high efficiency or greater, and those high efficiency values are determined from NEMA MG1 tables. They took those values and used them in the law. But there are many exemptions to this law, and some of the exemptions make a lot of sense. I'm just going to talk about really the concept of it is, when you're cycling a lot, like a brake motor, a brake motor is going to be cycling because it has a brake to cycle. If it's not a continuously rated duty motor, like if it's not an S1 motor, you're not going to be running it enough to gain energy back. Certain horsepower sizes, fractional horsepower sizes, are not considered to be using enough energy to make a difference, and greater than 200 horsepower motors are also not of a concern with this law, because as a motor gets bigger in size and design, the efficiency goes up. And once you get to a certain point, like 200 horsepower or greater, you really can't make them any more efficient. They're already efficient. So those are some of the exemptions that are in the EPAct. Now there's going to be a new law coming into effect in 2010, and that is called EISA. It's the Energy Independence and Security Act that will be in effect. A lot of the exemptions from the old Energy Policy Act are going to carry over, but some of them will not. All of the exemptions that I have listed in red over here, they do not carry over, but all of the other ones do. So here's an interesting question. Why are there only efficiency laws for motors? I can't answer that question. I don't know the answer, because really where you stand to make the most gains are in the mechanical portions of your system. Hopefully in the future there will be some laws regarding the mechanical portions. Of course there should be exemptions, but we'll talk more about the mechanical stuff next after the motor. Alright, the next part of the system we're going to talk about is the gearbox. This is a really big part of the system, and this is where we can stand to make a lot of gains in our efficiency. Some of the losses in the gearbox are going to be churning losses, mesh losses where the teeth actually come together, windage and seal losses. There's other losses too, but we're just going to concentrate on the ones that can make a big difference. If we look at the proportionality between the different losses in the gearbox, the majority of the losses come from the actual tooth contact, the meshing. And we also have churning losses, and we have bearing losses and seal losses. Seal losses, they can be minimized a little bit by using the correct lubrication, the correct amount of lubrication. Seals have to be lubricated. You could also use PTFE seals, which are it's a Teflon type of seal. and actually the seal wears away just a little bit, and some of the PTFE material is sacrificed and lays a little layer onto the shaft that it's actually sealing, which can reduce the friction a little bit. Bearings losses, they can be minimized a little bit by using low friction bearings, but more importantly, the proper amount of lubrication. If you put too much lubrication, too much grease in a bearing, you're going to make it really inefficient. Bearings need the correct amount of lubrication. For a bearing would be 1/3 full for a high-speed bearing, or for a low-speed bearing like your output bearing on a gearbox should be approximately halfway full of grease. So those are a couple ways you can minimize your seal and a bearing loss. The first big loss in a gearbox that we're going to talk about is the mesh power loss, or the tooth contact loss. I'm going to break gears up into two major categories. I know there's more categories than that, but for us today, it's good enough to talk about rolling type of contact teeth and sliding type of contact teeth. Rolling type of contact would be a spur gear, or a helical gear, or a bevel gear, or a helical bevel gear. This type of contact is much more efficient than a sliding contact, which would be like a worm gear set. Rolling contact gears are typically have a power loss of 1.5% per stage, and that's pretty good. A worm gear's power loss is actually dependent on a couple of different factors: the ratio and how many teeth are on the worm gear itself. For example, a typical worm gear that has one tooth on the gear, the efficiency could be between 50 to 69%, 2 teeth up to 79%, and 5 teeth up to 88%. So it really depends on how many teeth you have on the worm and what your gear ratio is going to be. The efficiency of a worm gearbox is inversely proportional to the ratio. So as the ratio goes up, your efficiency goes down. If you just want to compare rolling contact versus sliding contact, a sliding contact gear like a worm gear is going to be much less efficient. It's going to run a lot hotter. There's a lot more friction. There's a lot more surface contact. So there's a lot more losses. If you pick a rolling contact type of gear, you're going to have a much higher efficiency. You're going to save a lot more energy. So rolling contact gears are a lot more efficient than sliding contact gears. And while we're talking about gear contact and efficiency, I just want to briefly talk about synthetic versus mineral oil real quick. Synthetic oil is designed to have a lower traction coefficient. That means that the oil wants to stick together really well, so that way when the teeth come together and the oil is between the teeth, the oil doesn't shear apart. You want metal, oil, then metal again. You don't want metal on metal contact. And that's something that synthetic oil helps you to accomplish inside of your gearbox. So that lowers the amount of friction inside of the gearbox, and friction is what? Friction is heat. It also lowers the amount of noise that you have in your gearbox. So synthetic oil helps us increase our efficiency a little bit. Well, how much does it increase our efficiency? Remember, we were talking about rolling contact gears a couple seconds ago. We said that about 1.5% of power loss per stage. Well, if we use synthetic oil, we can get rid of about 30% of those losses. So we could reduce the amount of losses per stage of gearing down to 1% per stage. And that's pretty significant, a 30% difference in your gear friction losses per stage. Now, what does a 0.5% really give you? Because it doesn't sound like much. But let's just take a typical gearbox, for example. Let's say a 10 horsepower motor with a 3-stage helical bevel gearbox using mineral oil that's shaft mounted. You can see by the calculation up here, 75,394 kilowatt hours per year is about how much energy you're going to use just to run that. And that would end up costing $7,539 a year just to run that gearbox with regular mineral oil. That extra 0.5% of energy that you're saving, check it out with a different oil, a synthetic oil with the same motor, with turning the same gearbox. Now it only takes 74,222 kilowatt hours per year to run that. You can save a lot of energy, and actually you end up saving a lot of money too. You can save about $117 per year just in this one particular unit. I mean, what if you had 10, 20, 30 of these units in your plant? You know, that adds up to a lot of savings, a lot of energy savings, and of course saving energy also equates to saving money. One of the other benefits of synthetic oil is you can increase the life from 2 up to almost 5 times the life of the oil in some cases. So that means you don't have to change your oil as often. You don't have to buy oil as often. You don't have to do preventive maintenance on your gearbox as often. So that's another hidden savings using synthetic oil. Of course, the initial cost is more, but your long-term benefits, like your efficiency and the longer oil life, is going to make up for that initial cost in the long run. It's going to be more efficient for you. Now there's some other losses. Churning power losses. Basically, churning is the gears have to plow through the oil, and that creates a loss. It creates friction between the gears and the oil. So there's a couple of different factors that affect these churning losses. One is the size of the gear, one is the speed of the gear, one is the viscosity of the oil, the gear type, and also comes into effect. There's different types of gears. So all of these things affect the churning losses. One of the major contributors to churning losses is the mounting position. The mounting position of a gearbox really determines how much oil you have to have in it. So the amount of oil is going to determine how much friction is between the gears and the oil itself. If a gearbox is mounted horizontally, as the gears dip down into oil, they can carry oil up to the other gear that it's making contact with. If the gearbox is mounted vertically, you have to put enough oil in it that you reach all of the gear sets. So that's really going to determine the amount of losses that you have. With a particular gearbox, you're going to see that there's different efficiencies for different. Here are some measured values for a particular gear motor, a motor and gearbox combination, showing that the different efficiency levels for different mounting positions. You can see that a horizontal mounting position has the highest efficiency, and vertical mounting positions have a lower efficiency, depending on if your high-speed pinion is completely submerged in the oil or not. That's just another, not really a trick, but it's another thing that really affects efficiency in a gearbox is how it's mounted. So that can play a great part in your efficiency. We have one more part that's mechanical. After the gearbox, it's attached to a transmission element. There's a couple of different things that you could have. You could have a belt, you could have a tooth belt, you could have a chain, or you could be directly coupled with a shrink disc or a tapered bushing shrink disc style of mounting. There's different styles of transmission elements between your gearbox and the application. And there's going to be losses there. You're going to have friction, you could have stretch, you could have slip if your belt doesn't have any teeth. So of course that's probably going to be our worst choice for a transmission element, would be something like a V-belt. A V-belt is going to have the worst efficiency because not only do you have stretch, but you have slip, and that slip creates a lot of friction, and that friction is heat, and that's lost energy, so we don't want to do that. Chains and tooth belts are the best when it comes to having some type of external gear reduction other than the gearbox, but the best way to go is just direct mount using a shaft mount, because you're going to transmit 100% of the torque, and you're not going to have any losses there like you would with a belt or a chain. So the best way to go is always have a direct mount between your gearbox and your application, if that's at all possible. So let's now that we've talked about all of the different components of a system, let's just recap everything real quick. We have total system efficiency. All of the efficiencies of each individual component, they're multiplied together. So each little change in efficiency, each power loss, makes a big difference in the overall operation and performance of our system and how much energy we consume. So the efficiencies are multiplied together. Let's take a look at a real live system. one of my engineering counterparts for our company down in Australia had this customer who was using a motor with a V-belt and a worm gearbox, and that was turning a chain, which in turn was turning a conveyor. And what we tried to do was convince this customer to go with just use a right angle helical bevel gearbox. It's more efficient, and we can directly mount that gearbox right to your machine. We can get rid of transmission elements, and we can increase your efficiency. Look at the efficiency of that system at the top with the worm gearbox. All of those efficiencies multiplied together. Now this is using the same motor. 60.8%. Almost 40% of the energy that's put into this system is just wasted as heat. That seems like a shame. If you look at that bottom system, all we did was take the same motor, put it on a right angle helical bevel, high efficiency gearbox, couple that to the same conveyor, and your efficiency went up to 88%. That's a big difference. And to put things in perspective, that system at the top, 7.4 kilowatts was lost to inefficiency. How much is 7.4 kilowatts? Well, 7.4 kilowatts is enough to power 123 60 watt bulbs. That's a lot of energy. That's a lot of heat. That's a lot of light. That's a lot of waste that could easily be taken care of by maximizing your efficiency of your individual components, removing components when they're not necessary, optimizing your entire system, thinking about the entire system. Now, of course, that worm gearbox was cheaper initially, but if you think about the long run, it was a much more expensive choice for that system. And when you think about the total cost of ownership, the initial cost is only about 20% of your total cost for the system. Your follow-up cost, that's where you're really spending all of your money, and the majority of the follow-up cost is energy. About 90% of your follow-up cost is energy, because you buy that system, it doesn't just run for a couple days, you have it for years, and it runs every day. So each small increase in efficiency is going to save a lot of energy in the long run, a lot of money. So I thank you for your attention today, and I hope you have a good rest of the day. Thank you.